Welcome to the login node. This is Will. In episode 3, we brought the entire cluster online. Rocking Linux on all 6 nodes, the login node handling DHCP and NAT, passwordless SSH across the cluster. Everything's connected. But right now, if I want to install a package on all 6 nodes, I have to SSH into each one and run the command manually. And if I want to run a multi-node job, I have to manually copy my data to every machine first. This episode fixes both of those problems. We are adding 4 things: Ansible for cluster management, NFS for shared storage, Chrony for time synchronization, and FreeIPA for centralized user authentication. Let's start with Ansible. Ansible is a configuration management tool that lets you define what you want and apply it to multiple machines at once. Instead of SSHing into 6 nodes individually, you write a playbook and run it once. Ansible handles the rest. Ansible runs from the management node. Installation is one command: sudo dnf install ansible-core. Already installed on my system, but that's all it takes. One thing worth explaining is why Ansible lives in OPT Ansible rather than the home directory. Home is about to become an NFS share, which means anything in home is visible to every node in the cluster. Ansible's configuration file contains SSH keys and vault passwords. Those should not be sitting on a shared file system. OPT Ansible keeps them local to management only. The 2 files that drive everything are host.ini and ansible.cfg. Let me walk through them. Host.ini is inventory. It tells Ansible what machines exist and how to reach them. We have 6 groups: head for carrier, management for arbiter, workers for interceptor 1 and 2, GPU for Corsair 1, and visualization for observer. Compute and all nodes are combined group using the playbook. At the bottom, the var section sets the Ansible user and cluster-wide variables like the network subnet and domain name that Playbooks will reference. One thing to notice: arbiter has Ansible connection equals local. Because arbiter is a controller, it does not SSH to reach itself. It just runs tasks directly. Ansible.cfg tells Ansible where to find the SSH key, the inventory, and the vault password file. The vault is how we store secrets like FreeIPA password without putting them in plain text. The vault password file sits at opt ansible.ansible vault password with permission set to 600. Let me verify connectivity. Ansible all-m ping. All 6 nodes come back with pong. From here, configuration changes go out as playbooks. One command, 6 nodes updated simultaneously. All the playbooks for this episode are in the GitHub repository linked in the description. Now let's talk about storage. Right now, each node has its own local disk. If I SSH into interceptor 1 and create a file, then switch to interceptor 2, the file does not exist there. For a single node workload, that is fine. But for a multi-node MPI job, it is a problem. You need all nodes to see the same data. NFS, Network File System, solves this. One machine exports a directory over the network, and every other machine mounts it as if it were local storage. In our case, arbiter exports home, every node mounts it. You write a file anywhere in the cluster, and it is visible everywhere else. Let me show you what we set up. On arbiter, LS block shows Samsung 990 Pro partitioned with LVM into 4 logical volumes. LV home at 167 GB for user home directories, LV work at 251 GB for active project data, LV shared at 84 GB for shared software and datasets, and LV scratch at 251 GB for temporary job output. Each volume is formatted as XFS and mounted under NFS data. The home directory on arbiter itself is a bind mounting point at /nfs data/home. So Arbiter uses the same shared storage as every other node. We use LVM here rather than a single partition because it mirrors how storage is typically organized on real HPC clusters. You get separate allocation per use case and the flexibility to resize volumes later without reformatting. Showmount-E localhost confirms all 4 exports are active and accessible to the cluster subnet. The actual NFS server configuration, the etc exports file, the firewall rules, the Linux booleans, and the client mounts on all nodes are handled by the NFS setup.yaml Ansible playbook. Let me verify the client side. On carrier, df-h shows all 4 NFS shares mounted from Arbiter, Home, Work, Shared, and Scratch. One thing worth noting, the playbook reboots worker and GPU nodes automatically, but carrier needs a manual reboot after the playbook finishes since it is the SSH entry point. Without the reboot, the FS tab entries are there, but the mounts may not all be active. Let me create a test file here. I created a sample text file on interceptor 1. Now on interceptor 2, the file is already there. One write, visible from every node in the cluster. That is NFS working. Before we move to FreeIPA, there is one more thing we need, time synchronization. FreeIPA uses Kerberos for authentication, and Kerberos is strict about clock differences. If 2 nodes are more than 5 minutes apart, Kerberos will reject the ticket and authentication fails. On a fresh cluster, this is usually not an issue, but it is worth setting up explicitly. The Chrony setup YAML playbook sets a carrier as an NTP server for the entire cluster. Carrier syncs from external sources like Cloudflare and pool.ntp.org, and all other nodes sync from the carrier. After the playbook finishes, every node in the cluster is on the same clock. Chronic tracking confirms interceptor 1 is syncing from carrier. Now we can safely move on to FreeIPA. Shared storage is solved, but there's a second problem that NFS actually makes worse. Let me explain. NFS does not care about usernames. It uses numeric user IDs or UIDs to handle file permissions. If I create a user called Will on interceptor 1 and the same username on interceptor 2 in a different order, they end up with different UIDs. Now those 2 users see different permissions on the same NFS files, even though they have the same username. You can work around this by manually synchronizing UIDs across every node. On a 6-node cluster with a couple of users, that is annoying but possible. On a real cluster with dozens of users or even more, it falls apart completely. The solution is centralized authentication, one place where every user account is defined and every node pulls from the source. FreeIPA does exactly that. FreeIPA bundles LDAP for the user directory, Kerberos for authentication, and its own DNS and certificate authority. It runs on Arbiter and was installed using the FreeIPA setup YAML playbook. Let me check the current status. IPA-CTL status shows all FreeIPA services running. You can see directory service, kadmin, named, httpd, and all in running state. Everything is up. If I get a Kerberos ticket as admin and run IPA user find, I can see the existing users in the directory. Notice the UID. FreeIPA assigns UIDs from high range, well above local system accounts. The exact range depends on your installation, but whatever it assigns will be identical on every node in the cluster. One thing worth mentioning about the DNS setup, you might expect that enrolling nodes into FreeIPA would require pointing the cluster DNS at Arbiter. In our case, it does not. Carrier's DNS mask handles DHCP and external DNS. When the nodes need to find arbiter.cluster.local for a FreeIPA enrollment, it looks it up via etc host, where Arbiter's address is already listed. FreeIPA enrollment adds that entry automatically. No changes to DNS mask were needed. Let me show you the full user creation flow from start to finish. First, I get a Kerberos ticket as admin. Then I run the user creation script from the repository. This script handles the complete process. It creates a FreeIPA account, retrieves the UID that the FreeIPA assigned, creates the physical home directory on /NFS data/home with the correct numeric ownership, applies the XFS storage quota, and adds the user to Slurm accounting for when we set that up in the next episode. Let me run it now. The script talks to FreeIPA, gets back the assigned UID, creates a directory with that UID as the owner, and sets the quota. All of that runs on Arbiter, but because home is NFS mounted everywhere, the directory is immediately visible on every node. From Carrier, I SSH as a new user to Interceptor 1. First login triggers auth job D to create the home directory entry. Same UID on both nodes. Different physical machine. NFS handles the files, FreeIPA handles identity. Any user can log into any node and find their files with correct permission. You install S-Shuttle on your local machine, add Arbiter's IP to your local etc host, run S-Shuttle pointing at Carrier, and then open the FreeIPA web UI directly in the browser using Arbiter's hostname. This gives you a full UI for managing users, groups, and access policies. For everyday user management, I use a script, but the web interface is useful when you need a full overview. Let me pull back and look at where the cluster stands now. Carrier is a login node. Users SSH in here. It handles DHCP and NAT, and it is the only node with the path to the internet. Arbiter is a management node. It runs FreeIPA, hosts the NFS storage on the Samsung 990 Pro, and will run the Slurm controller in the next episode. Ansible also runs from the Arbiter and manages configuration across the whole cluster. The 4 compute nodes are clients of both NFS and FreeIPA. They mount home from Arbiter and authenticate through FreeIPA. Any user created on Arbiter can log into any compute node and find their files exactly where they left them. This is the same architecture pattern used in university research clusters. The scale is different, but the pieces are the same. Shared storage, centralized auth, and the management layer that lets you treat the cluster as a single system. All the Ansible playbooks and the user creation script from this episode are in a GitHub repository. Link is in the description. The blog post has a full step-by-step breakdown with every command if you want to follow along. In the next episode, we install Slurm. With NFS and FreeIPA already in place, Slurm has everything it needs to schedule job across nodes, track resource usage, and write output file back to the shared storage. That is when these clusters start feel like the real thing. Hit subscribe, and I'll see you in episode 5.